Hi everybody. As mentioned in class, we neglected accidentally to put uniform circular motion, the material from chapter 10 that we covered weeks 1, 2, and 3 in this class this semester on the review packet. I'm going to give you a quick review of the concepts involved, and then we're going to do the problem set together that I gave this week in class. Simply put, uniform circular motion is circular motion, an object moving in a circular path of constant radius at a constant speed. Because you're traveling in a circle whose radius is constant and your speed is constant, then the time it takes you to go one revolution is constant. Something about circular motion that is mysterious to many, and was to me in high school, is that even though your speed is constant, your velocity changes and you are therefore accelerating the whole time. Not only are you accelerating the whole time, but a force is required for this type of motion, a so-called centripetal force, center-directed force. As we said a minute ago, the object's moving around a circle. At the instant the object is here, its velocity points down and to the right. But a moment later, if it's going clockwise, let's say, the object is now here. And its velocity, which is always tangent to the circle, now points in a different direction. The change in velocity means it's accelerating, and that acceleration is toward the center of the circle. That acceleration is given by the formula v squared over r. Now, the speed of the object is simply the distance it travels divided by the time it takes to travel that distance. For a circle, the distance that's relevant is the circumference, 2 pi r, and the time that's relevant is a special time called the period, the time for exactly one cycle. This is not 2 cycles, this is not 5 cycles, it's 1 cycle. Lastly, where there's smoke, there's fire, and where there's acceleration, there's a force. And the centripetal force is equal to ma, and since a is v squared over r, ma becomes v squared over r. Those are the formulas. I'm going to go through the problem set that we added to the midterm review real quick with you and keep this short and sweet. Thank you. So here's the problem set real quick. And it's just a chance to get you to remember those formulas we just went over on the board and remember that you know this material. A 0.452 kilogram yo-yo, so that's our mass, is moving at a constant speed around a circle that is 0.45 meters in radius. The yo-yo makes one revolution in 0.37 seconds. So our list would look like this. The mass was 0.452. The radius, 0.45. And the period, the time for one complete revolution, capital T, is 0.37 seconds. What's the speed of the yo-yo? Well, the speed, of course, is the circumference, the distance around the circle, divided by the period. I'm going to plug in those values quickly. Using the calculator, 2 times pi times 0.45 equals, divided by 0.37 equals 7.642 meters per second. So now we have the velocity written down as 7.6 meters per second. Now we want to find the acceleration of the yo-yo that's moving in a circle. As you know, the acceleration that we call the centripetal acceleration directed toward the center of the circle is equal to the speed squared over r. So let's go ahead and set that up. Inside the top parentheses, I'm going to put 7.642, the unrounded version of my speed from part A. I'm going to remember to square that. And I'm going to divide that by r, the radius. The radius was 0.45 meters. I still have the velocity, or speed I should say, in my calculator, so let's go ahead and just square that. Divide by 0.45 and hit equals. The answer comes out 1.29768. I rounded that to 129.8 just to write it down. And then because of sig figs, I rounded it finally to just 2 sig figs, 130. Last, we're asked to find the centripetal force on the yo-yo. Centripetal force is mv squared over r. Another way to write that is MAC, because AC is v squared over r. Since we have AC already in our calculator as well, why don't we just go ahead and multiply the answer we got here by m to get F equals ma. The mass, you'll recall, was 0.452. Let's go ahead and put in 0.452 kilograms and multiply by 129.8 meters per second squared. Of course, that number is still in the calculator, so why bother rounding off? I'm just going to hit times 0.452, and the answer comes out 58.655. Kilograms times meters per second squared is newtons, and rounding that off to just 2 sig figs, I get 59 newtons. The last question here, or the next question I should say, asks us why is it true that an object that is moving in a circle at a constant speed is accelerating? Well, you'll recall that acceleration is the change in velocity, which is a vector quantity which has direction and size, speed and direction. Acceleration is change in velocity over time. Because the direction of the velocity is always changing, we have acceleration. And in what direction is that acceleration? Well, we've talked about this a lot. It's toward the center of the circle. Let's take a quick look at problem 3. We have some numbers given. Let's write them down. A 2.1 kilogram textbook, that's my mass. It's tied to a string and whirled around a horizontal circle at a constant speed v of 6.9 meters per second. And then they say if the time to make a single trip, time for a single trip, well, that's the period, and that is given to be 1.4 seconds, what's the acceleration of the textbook? Now, the only equation I have for acceleration is v squared over r, and I don't know r. So at first I think I'm stuck, but then I realize that speed in circular motion is 2 pi r over period, and we know the speed, we know the period, and we know 2 pi is just a number, a constant. So let's rearrange this real quick. I'm going to multiply both sides by t. We get v times t equals 2 pi r, and now dividing both sides by 2 pi gives us r equals vt over 2 pi. And I can plug in the values for v and t. There's v, there's t, and I can divide that by 2 pi. Now watch how I do this on the calculator real quick, because this can sometimes be an issue for some of us. When you do the numerator, you just multiply and hit equals. So 6.9 times 1.4, no problem, equals 9.66. But when you because the bottom is 2 times pi, I'm going to divide, numerator, divide, and I'm going to open the parentheses. Opening the parentheses allows me to say 2 times pi, and then close those parentheses. There it is. There's 2 pi, 6.28. And now I hit equals, and I get a radius of 1.537 meters. Okay, now I can go ahead and find the acceleration. Acceleration is v squared over r. So in this case, 6.9 meters per second squared divided by that r we just found using the velocity equation solved for radius. And it came out 1.537. Another little trick using these calculators, the thing that I want on the denominator is on the screen. So I'm going to store that, STO1. you'll notice that if I hit recall 1, it's there. Even if I clear it and I hit recall 1, it's still there. So that's useful. Let's go ahead and put in the 6.9 meters per second, square it, and now hit divided by recall 1 equals, and there we go. The acceleration comes out 30.967. That's going to have units of meters per second squared, and rounded off to 2 sig figs, that's going to be 31. Okay, so let's just finish up these last two parts B and C to the problem. Part B states that now you whirl the textbook at twice the original speed, but nothing else is mentioned. So I think we can assume that the radius remains 1.537. Say the mass is not going to change. So we're asked, if we double the speed, what's the effect on the force required to do this? Well, again, the centripetal force that allows an object to move in a circle is always equal to the mass of the object, the speed squared over r, mv squared over r. In this case, it's the same textbook, so the mass doesn't change. So I'm just going to leave that as 1. Let's just pretend it's 1. And the radius hasn't changed, right? So let's just assume that let's just pretend it was 1. If these don't change, the only thing changing that can make force change is the speed is changing. And so the result of this realization that the only thing changing is velocity, we realize that the force is proportional to the square of the velocity, because in the equation, speed is squared. So if we simply double the velocity, or the speed, I should say, really, but if we double it and that quantity is squared, that results in a 4-fold increase in the other side. I mean, if this goes up by if this whole thing goes up by a factor of 4, which it does when you double speed, then force will be double squared, or 4 times, I should say, the original force. So our old force goes up to 4 times its original value. Lastly, if two textbooks, which would double the mass, so we're changing the mass from m to 2m, are tied to the same string and whirled at the same original speed, what's the effect on the force required to do this? Well, again, force depends on, the mass. You're moving in a circle, the speed squared at which it's moving in that circle, and the radius around which it's moving in that circle. But again, if they don't change the speed and they don't change the circle's radius, then m is the only thing that can change f in this case. So force is proportional to whatever the mass is doing or is. Because we doubled the mass, that will require a doubling of the force. And so the answer I'm hoping you are comfortable with is the force will double to 2f if we double the mass and everything else stays the same. Thanks a lot for watching. Hope you're having an okay time getting ready for the midterm, and we'll see you tomorrow.